Hi everyone, I'm Lorenzo De Donatis. I'm managing the ICL consultancy division in Ireland for IES. ICL will make more sense for who is not familiar with it in a moment. So it's basically our set of tools that we use to try to digitalize the built environment and decarbonize it, hopefully. So what I'm going to speak today is how we are using our tools. So first of all, I give a very brief introduction of who we are and what our tools are for who is not familiar with them, just to give a little bit of context. And then I'll jump into a couple of case studies that will be probably the most interesting part. And I'll touch upon something that also Mary has mentioned there in terms of like the importance of collecting the data, of really having that sort of building passport and having the data handy to actually enable this digitalization of the built environment. So just briefly, we've been in the market for the last 29 years. We've been doing energy simulation and energy analysis. So we have a consultancy team in IES, which will do all the consultancy projects, but we also sell our software elsewhere. So most of the companies that will do energy simulation and energy modeling will be using our software. And Apache that you see there is kind of the engine, the physics-based engine behind the energy simulation. So basically all the physics equation, the heat flux and everything is coded into that Apache engine. In terms of our mission, obviously I'll be very brief on this because it's the mission of everyone that is here. Probably we're trying to decarbonize the built environment, and really what we're trying to do and the challenge that we're facing is trying to digitalize as much as possible this project to make it possible to scale it in a much better way than we've done in the past. So one of the problems in buildings that really we've seen in the past decades, and that we've seen not only through digital but also in general. So if we imagine that curve there, at the top of that curve we could have the better performance of the buildings, and the bottom is like a worse performance. So what we've seen is that digital has always been used for buildings, but mostly at compliance stage. So we would have a compliance stage model where basically it tells, okay, your building is going to perform very well. It might be a lead model, it might be a BER, any assessment really. Once actually the building is going into construction, like detail design, construction, commission, you start seeing that problems start to occur. You might go into construction, the budget starts to be cut off, so you are in the lower range of that optimal design that you were hoping for. Then you go into commissioning. We would have spoken with a lot of building facility managers and commissioning managers over time and trying to understand what their problems were. A lot of that work is reactive work. So they will see a problem. They try to understand what the problem is. Sometimes it takes 2 weeks to realize that the fan of your ASU might be clogged. So you have a problem. For 2 weeks, you'll just waste energy, and you realize that afterwards, and you wasted energy for a long time. You go into building operation. You deliver your building to your owners. Most of the time, they don't know how to operate that building. They don't know the best way to operate that building, especially if there is not a facility manager. Let's say it's a residential building. They are not really explained how to best operate that building. So you start getting worse and worse. The solution really that we see there is using digital. So instead of leaving that model there, the compliance model there, which is what we kind of call sleeping digital twin, which just sits there, no one uses it, and it's just telling you your building should perform like this, but it actually doesn't. So the solution really is just taking that model and bringing that with us during the phase of the construction of the building. So the model should get updated at construction stage. You update the information with the actual as-built information that you have, and you really see your performance going on. Why? Because, for example, at commissioning stage, that same model, and I'll show you some examples afterwards, can be used to actually analyze your data and understand straight away what your problems are. Say, for example, your temperature in a room drops below a certain point, your model immediately tells you, look, the temperature here should be 24 degrees, it shouldn't be 25. So the facility manager doesn't need to wait for someone complaining for the temperature and then start to look at what's happening. You can use the model. There can be alerts from the model that directly tells the facility manager or the building owner, look, there is something wrong here. And through the model, they can immediately understand where the problem is. And the same goes then in building operation. So say, for example, we are in a residential building. If you have a detailed digital twin, an energy model, I'll show you in the next slide what exactly we refer to as a digital twin. But basically, the model could also tell you, by using machine learning and AI, it could also tell you, look, tomorrow actually the weather is saying that the temperature is going to be lower than today. So maybe you should start your heating on tomorrow at 6 a.m. rather than 7 a.m. And you can save in that case energy, because your occupants, once they get into the building, they don't start feeling cold, and they don't just bring that temperature set point to 28, 29 degrees just to feel warm, and then maybe they leave it there for the whole day. So really this kind of interaction between the model, the commissioning managers, and the operators of the building should be more straightforward. Just in terms of what is a digital twin, so basically we have that physics-based model, which is what we have always done in energy modeling, but then we add to that all the data that luckily today we have available. We have IoT data, we have BMS data, so there shouldn't be a difference and a complete separation between this data and the building. Everything should be integrated, and we should make the most use of this to create what we call this digital twin or hybrid model, so hybrid between real data and physics-based data, and create this digital twin. So just quickly on our products, you might be familiar with the VE, which is the virtual environment, which is the energy modeling tool that we've always used for the past 29 years to build energy model of single buildings. But now we are expanding that for city scale models, which could be communities, which could be full cities, and I'll show an example of that. And the concept is the same. So behind this, there is always that Apache engine, so that physics-based simulation model, but we are trying to scale it to whole cities and campuses. Then the IceCam platform, which is for data analysis, which I was mentioning before, to kind of try to help facility managers or building operators to understand where possible issues lie in the buildings. And then virtual networks. So we also look, for example, at renewable energy at scale. We look at CHP plants or any asset that could be at community level. So rather than looking at the building itself, we start looking at district heating networks, grids. So, for example, say we want to install large-scale renewables. We also want to understand, okay, what's the impact on the grid? Can the actual infrastructure accept that additional generation? So, who is the tool for? For building owners and operators, for cities or public authorities who want to create a roadmap to go to net zero or divest from fossil fuels, or utility and network operators which want to look at designing heating and cooling networks, or just to see the impact of policies and renewable energy integration into the grid. Now I think that's enough just to give again some context of who we are, and I show a couple of case studies. So the first one really will be a building scale decarbonization study that we've done in collaboration with Dublin City Council. So basically we've taken as an example this building, which is in Dominic Street in Dublin. Basically, this is a social housing. The conditions of the buildings are not great at the moment, so the city council is looking for possible renovation of the buildings. It's vacant at the moment, so it's easy enough to think about potential retrofit strategies. Obviously, given the condition of the building, the strategy 1 and 2, we analyzed 4 different strategies. The shallow and medium retrofit, which normally those percentages are, let's say, an indicative way of saying how much energy could you more or less save through those strategies, but we will see that through the tools we actually went into more detail for those numbers. Really, what they were interested for was more strategy 3 and 4. So will the deep retrofit or a full renovation, which is basically reducing the building to the structure itself and just rebuilding it completely, what's really more efficient from an energy and carbon impact perspective? And we not only looked at the operational side of things, but also at the embodied carbon to have an overall picture of the impact of the study. So how did everything work? So we started from a site survey. So you can see from the picture that the conditions of the buildings weren't great. We collected all the information that we needed, and we created digital twins for all the 3 blocks there. Then we analyzed one block, specifically the one in the middle. They are all identical between each other, and through the energy model we assessed that the difference in energy performance would be less than 1%, and that's mostly for the solar shading assessment, that small difference. So once we created that digital twin, and again we used the geometry information, construction, the heating and cooling plants, and so on, but really this was a tough work because, and again, I want to link back to that building passport that Mary was mentioning before. If we were to have a building passport with all this information across all the buildings, and this is something that other industries already do. If we go into the automotive industry, there is no way that someone says, okay, I need to find the information about this car. You already have them available. So ideally, to scale this, we will really benefit from digitalizing the built environment. So tough work was collecting all those information, especially for older buildings. They're not always available. Once we did that, we started analyzing the energy demand and carbon emissions from an operational perspective with our tool, the virtual environment. And then we analyzed in parallel also the embodied carbon impact through one-click LCA, which is something that also Mary's mentioned before. We have an integration within our tool with one-click LCA, where basically we can export our building in one-click LCA, and one-click LCA has a database of embodied carbon impact of materials. So we use that information to also study the embodied impact of the renovation strategies that we are considering. From an operational perspective, the energy model was able to give us a good breakdown of the baseline energy consumption. You can see there that most of it will be space heating and hot water, and a good portion of that will be also addressable to lighting and equipment. Once we were able to understand this, really, we were able to then say, okay, what are the best strategies to start to retrofit the building? And I'll show the results in a bit. Before that, I want to show also the embodied carbon part. So in the embodied carbon part, basically there are two ways in which we analyze the embodied carbon. One, you can see that per building element. It's a bit small there, but you can see that, for example, within the retrofit strategies, a good part of that embodied carbon will be addressed to the plants that are replaced. So, for example, replacing the current boilers with the heat pumps to improve the carbon behavior of the building, especially in time, because the grid is starting to decarbonize. So we will see that we did an analysis in the next 60 years, also using the projected factors for the electricity grid's emission factors. So basically you can see a big impact is not only on the structure of the walls themselves, of the insulation, but also on the plants and the replacement of the plants over time. And also we did a similar analysis per life cycle stage. So you can see that most of that embodied carbon is coming from the materials themselves, and the part of this the part of it, especially for the full retrofit, is for the replacement of plants and materials over time, because obviously if we do a 60 years life stage analysis, obviously your heat pumps and so on will need to be replaced every 30 years. Once we look at the overall picture, we can say, okay, we look at the various strategies, we look at the baseline, we look at the other shallow, medium, deep, and full renovation, and let's look at the operational embodied impact. So obviously, as we were expecting, the operational, the EUI is the energy usage intensity. So obviously, in terms of kilowatt hour per meter square, as we were expecting, the full renovation is the best option. But then if we look at embodied carbon, really it has a large impact. It's about double or even more the deep renovation one. And that's just an indicative BR, as in saying the energy consumption of the building will more or less behave like an A3 building if we went for a full renovation. What's difficult to say there is, okay, from this picture, so what's the best option? So should we go for a deep retrofit to minimize the embodied carbon? Should we go for a full renovation, or should we leave the building as is? So really what we wanted to plot was, okay, what about the whole life stage of the building? So if we look at the next 10, 30, and 60 years, and really 60 years is what we're interested in, especially if we go for a deep renovation or a full renovation, because that's the life cycle of a building. You can see that the light green ones are the operational emissions and the dark green ones are the embodied carbon emissions. So really what we can see is that despite the full renovation has a very low operational carbon impact, in reality the best solution in this particular case is the deep retrofit, because overall if we sum the embodied carbon and the operational carbon, we have a lower impact from the deep renovation, and obviously all the works are also cheaper and easier to do. This might not be the answer for a different building, and that's why really we need digital to be able to plot these numbers and not just do, let's say, an average number that will be relevant for all buildings. Another thing that we created as as part of this project was this dashboard, because it's important also to communicate the results. We can do all the complex analysis in the background, but then really it's important that the city council or whoever is the client then communicates this to their stakeholders to show the value of this. We've created this dashboard, which I opened earlier just to make it quicker. Let's see if I can have it here. So basically this dashboard is a way of showcasing the results. We have this homepage there, which kind of gives a summary of what I said already. And then In the next page, really, what we can do here is showing what's the impact of all our strategies. So it's in an interactive way of showing, okay, if we select a certain strategy, if we go for a deep retrofit, if we go for a medium retrofit, what's the impact of that? On the top right, we can see the whole life CO2 emission of the baseline against the selected strategy, and I can plot that against 10 years, 30 years, and 60 years based on really what I want to plot. The investment cost is just indicative because as part of the project, we did analyze costs as well, but in agreement with the Dublin City Council, we just left an indicative cost between 0 and 4 in terms of low and medium and high. So this is just an example, and there is a full report that is also accessible and it's public. So if anyone is interested, it's on the website, or just send me an email afterwards and I will share with you. And we also created a 3D model for the City Council to be able to actually access their model. Basically, we've created a model of the whole Dublin city center, and then more in detail, we did create models for those 3 buildings. So basically, this model, it's loading in a bit, probably the Wi-Fi is a bit slow, but basically it's a way, again, of accessing results, and also potentially in futures to start mapping anything else against those buildings. So if I go here, for example, I can zoom into Dominic Street West buildings. You can see the 3 buildings there. I can click on a building and I can start looking at, I can start looking at all the KPIs that I was showing before. So you can see what's the floor area of the buildings, what's the BER, the operational energy use. If we have live data from if someone then in the future says, okay, I'm a building owner, I want to map my meter data to this model, they can use the same model to map meter data, and they can have their own dashboard, which is private, obviously, if they don't want others to access their building data. And they can all have everything in the same platform. So that's really the digital transformation that we are going through. And in this, they can also say, okay, for example, I want to analyze a comparison. I want to say for this specific block, I want to analyze what happens in my shallow, medium, deep, and full renovation. For example, I want to compare only the deep and medium retrofit. And let's say for block B, and I want to compare in terms of carbon. So let's say embodied, or let's say total carbon at 60 years. So I apply this and I can actually see, okay, how is my carbon being impacted from the baseline scenario to the retrofit and scenario for full renovation. So it's an interactive way, again, of visualizing all the results. Going back to the main presentation, I'll quickly go through the second case study. So basically, this second case study, I will really fly through the first 3 slides because the first 3 slides are about a case study that was shown last year. But what I will focus on are the last couple of slides that is kind of a follow-up of what we've done. So basically, just to give a little bit of context, this project is part of an R&D project. It's called City Exchange, and we've created all the model for the city center, the Georgian district of the Limerick city. What we've done was basically saying, okay, we want to help the city council and we want to help the city to map their policies over time and to try to understand how they can decarbonize the city center according to the current policies. So will they reach net zero? Will they not? What else should they do? So those are the first 3 points. And what I will focus on later, the yellow points on the bottom there, is after that we started looking at a single block in particular, so 5 buildings, and we started looking at how we can monitor and measure the performance of those buildings through energy meters. And there I will show a little bit of that digital twin concept that I was talking about before. So very briefly, we created a model of the whole city center. You can see the division between public, commercial, and residential buildings. In this case, we have collected all the information from the city council, from SCI public BER databases, anything really that we could collect based on the building age, based on the type of buildings. We started to collect U values, type of plants, fuels, and so on, and we mapped the energy use of the building of the baseline. And after that, we said, okay, we need to map actually the policies. So we took the policies, we started saying, and again, I will go quickly through this, but I can send more material afterwards. So we started saying, okay, we add electric vehicle chargers to the model, and those are not just visual, those are actually energy consumers in the model. So every energy consumer, every energy generator is mapped through the model. We started saying, okay, we add PV panels according to the climate action plan. We started retrofitting the buildings, starting from the worst performing ones. So you can see on the top left there how the energy usage intensity decreases overall in the city as we retrofit more and more buildings. And it's also a way for the city council to say, okay, we need advice on where we should start retrofitting, which buildings should we start retrofitting first, and where should we go. So very quickly go through the end. In 2050, you can see that the 3 lines are representative of the total carbon emissions, and then the orange and blue are transport emissions and buildings emissions. So we mapped all of that, and we said, okay, we can achieve about a 70% reduction in total carbon emissions with the current policies, but that's really a sign that we should do more. So the current policies sometimes might not be enough. We should push even further, and that's a brilliant way for a city council to say, okay, take all this paper that you have and translate that digitally and see where actually we can get. And as I was saying before, what I wanted to also focus on was a little bit more insights on these 5 buildings. So what we've done was, once we've done that large scale analysis, which again needs to be taken as a guidance, so all these models have a higher level type of information. Then once you go and say, okay, actually I want to take this building and retrofit this building, and I want to measure and verify the performance before and after my renovation. So you start doing energy models of those 5 buildings. In this case, it's a mixed-use block, also because the idea was to turn this into a positive energy block where the buildings potentially could share energy. We'll say, for example, there is PV panels on the rooftop of a residential buildings. Maybe there is no one in the residential buildings during the day, so that energy, instead of being wasted or feed back to the grid, this can go and be used from a commercial buildings nearby. That's the kind of idea behind the positive energy block, and that's where also the concept of a virtual network comes to play. In this case, for example, we are looking at some sensors and IoT that we installed in one of the buildings. You can see here the illuminance level, CO2 concentration, temperature, relative humidity, and these are the various rooms. So really what's powerful here is that all these dashboards can be accessed directly from that same digital twin. So let's say a facility manager, for example, might be interested in looking at, okay, what's the CO2 concentration in this particular room? If they see that there is a peak, they can immediately say, okay, there is something wrong here, and they don't need to wait for someone to complain about that after 1, 2 days or a week. So there is an immediate way for them even setting alarms and saying, okay, there is something wrong here, let's go and fix it. And even more interesting is probably the next slide, this one. This is an example of energy monitoring. And so here we are monitoring electricity specifically for a building. So you can see that the green lines are from the energy meter. You can see there are a lot of gaps there, which is not something rare. It actually happens often. It might be connection issues of the smart unit. It might be Wi-Fi issues. It might be anything. In this case, there were constructions nearby that caused the issues. So really, the power of the digital twin is then go and say, a building owner here could say at the end of the month, oh, that's great, I consumed less energy than last year, but they wouldn't realize that probably it's just because some of the times during the day or during the month weren't considered. So at the end of the month, they might receive a bill and saying, oh, there is something wrong, I consumed less than last year, why is my bill higher? So the power of the digital twin there is really filling those gaps. You can see that in this case, we calibrated very well the digital twin to be representative as much as possible as of the building usage. And the purple ones are the values that are replaced from the digital twin. So whenever there was a gap, we created this concept of a hybrid digital twin, which uses live data as much as possible. But whenever there is a gap, and in this case, it's about 15% of the time in this time frame, replace that gap with the digital twin data. And what this allows is then to map reliably the consumption of the building over time. So there is no, let's say, misunderstanding between your energy bill. There is no performance gap between your energy bill and what you're actually seeing on your dashboard. In this case, this was useful also because then we mapped the current energy usage of the buildings against the expected. So this line in the middle is the expected consumption of the buildings from the energy model. And the green line is the energy usage over the last 365 days. So you can see that in this case, all the buildings seems to be performing better than they should. However, we need to consider also COVID period. So obviously the digital twin is expecting the buildings to be fully occupied. Most of them are not. So that's a sign of saying, okay, if my building is occupied a third of the time as it should, and it's consuming almost the same, then there is something wrong. But really, without the digital twin, the consumption of those buildings might be way lower than that, and the owners might not know the reason for it. Before I go into the summary, just very quickly, I opened here also the model. So similarly to what we've said before, we've created a model for the whole Limerick city, which is this one. And through the model, previously I've shown some KPIs, but really through the model, you can potentially visualize anything, input, output data. So in this case, I'm showing the building energy usage intensity in kilowatt hour per meter square of the whole city. Then you can go and zoom, for example, in a particular block, which is the block that I was showing beforehand. And then you jump into a building and you can say, okay, actually, I want to look at the consumption specifically of this building. In this case, we are showing the monthly energy consumption in terms of total energy and total carbon emissions. So anything that we want to display here, whether it's energy, whether it's, for example, vacancy data was something very important for Limerick because a lot of these buildings are vacant. So it's a good way for them to just through a button click and map their data and then visualize, okay, what are the what are the main vacant buildings in my city? So what should I address first when I go and address the policy of retrofits? And also there is that concept of the private dashboard that I was saying before. I won't go into this because it's private data, but the building owner will have his own private access to their building dashboards, or a facility manager, or whoever they want to give access to. So through the same model, they can then go into another layer and look at those live data and try to understand those data and make sense of those data again. This very last slide and I'm done. So just as a summary, so as a summary, really, the concept of the digital twins for the built environment, really what we are trying to do is optimize, first of all, optimize the performance of the buildings that we already have in the built environment, because obviously we can try as much as possible to make new buildings perform better, but first of all, we need to optimize the consumption of the build and the energy behavior of the buildings that are there already, and not only buildings, but also communities and networks. We want to balance energy and carbon. Also, we've spoken a lot about ESG targets, so that's also something that through digital we can look into. We can build dashboards for clients or for whoever wants to report about that sustainability concept in general. So not only detailed and digital twins, but also depending on the stakeholders, we can address different targets and then really plan for the future and track your progress, because we can plan. We can use the policies, but then it's important to track that progress and not forget in 10 years where we were expected to be today. So really, that's important to use the same twin to then map the progress over time. That's pretty much it. I don't know whether I was very quick, but I wanted to kind of show everything and not steal too much time to Michael, the next speaker. But for anything really that you're interested, again, there is that public report of that Dublin City Council project with a lot of data behind it, or anything else that you're interested in, please contact me, and that's my contact. Thank you.
Thank you, Lorenzo. It was great. Thank you very much.